All right, so lecture 14, we're gonna continue with the Chinese remainder theorem. We'll give the proof and we'll start working on the applications for it to bring all these base cases that we've had before and put them all together. And then my plan is to wrap this number theory results hopefully by the end of today, but I think it might spill into the next class lecture. But for the next lecture, I want us to, after we're done with this, before we go to the quantum Fourier transform, and the Shor's algorithm going through it, I want us to do a discussion section, and it's going to be on the latest articles that you've shared, and it's going to be focused more on starting the class project and get us going on that. And so let me remind you quickly what the Chinese remainder theorem says, is that there's a bijection between integers modulo n and this tuples of integers modulo pi to the alpha I, where the prime factorization of n is given by the pi's to the alpha i's. And not only is there a bijection, which since the two sets have the same cardinality, there should be and there are many, but there exists a specific bijection that preserves the additive and multiplicative structure. So this is the main content of the Chinese remainder theorem, that we can, instead of doing the math on the left-hand side, we can do the math on the right-hand side and break it up into pieces. So we can just work, the base cases that we work on are these smaller cases, and then we generalize by the Chinese remainder theorem. So this is how we can glue all our results together. So what we started doing in the previous lecture is we started checking this for a specific case, and we checked the additive structure. In here, the Chinese remainder theorem is this statement, this bijection, and the bijections are the going forward, the map going forward. You just project your x into modulo 2 and modulo 3. So you just take your x and you just mod it by 2 and mod it by 3, and that's how you project. You go from this side to this side. And this is important to keep in mind when we're gluing our results together. We want to know how to go from the left to the right. This is going to come back. And so, but the map is straightforward. It's just take mod these numbers. And then going back is a little less trivial. In here, for this specific case, this is the formula. And to actually give the proof of the Chinese remainder theorem, we're going to come up with this formula to map things back. So here we check the addition table. Let's check the multiplication table. So I'll give you some time to work on the multiplication table. And here, if you're multiplying a tuple, alpha 1, alpha 2, and you multiply it times beta 1, beta 2, then it's going to be equal to alpha 1, beta 1, alpha 2, beta 2. All right. Is this what people got?
You're working on the right.
I was getting there, yeah.
I started after you guys a head start.
Yeah, that's what I got.
So this one should be straightforward. I started just filling out with. So I assume you guys finished this.
It's pretty close.
Yeah, pretty close. And how far did you guys get in this? Almost there. Yeah. So in here, ideally one has to check that using this dictionary, which is just this and this, that everything here agrees with everything here. It's satisfying to check the zeros. Zeros, 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 zeros. Where else do we see zeros? Zero. So 0, 0, 0, 0. There's this kind of like circle of zeros. So we have this circle of zeros. I kind of satisfy just by looking at the zeros. And you can go check more things. So in here, we're checking by hand that the multiplicative structure and the additive structure is preserved under this mapping, under this bijection. So this is the statement of the Chinese remainder theorem. Now, and I wrote the solution here. Now, here we have a case where the Chinese remainder theorem doesn't apply, where the multiplicative structure is not preserved. And in the statement of the Chinese remainder theorem, we can only simplify things up to a prime to a power. We cannot decompose the prime even further. So in here, to show that the statement is non-trivial, let's consider this case and show that, and try to see that there is no bijection that preserves the multiplicative structure of the left and the right-hand side by just showing that the multiplicative structure of the left and the right-hand side are intrinsically different. So in here, let's do the multiplicative structure. Let's do the table for the left side and do the table for the right-hand side. And again, multiplication is component-wise. So let's do that. And smaller case, smaller numbers, so that's good. Mm-hmm.
So with the last example, I didn't really know how you were ordering the stuff on the right side, like the numbers, like the 0, 0, 1, 1, 0, 2, like that. It's not immediately clear.
So I take this 0. It's by this map, essentially.
Oh, okay.
So 0, I take mod 2, mod 3, and it's 0, 0. And I take 1, mod 2, and mod 3 is 1, 1. I take 2, mod 2 is going to be 0. And mod 3 is going to be 2.
Yeah.
So it is a weird, it seems like a weird ordering, but it was by this map so that the tables would match exactly. If it wasn't ordered the same, the tables wouldn't match exactly.
Okay, that makes sense.
And that's a question for the next one. Can we reorder the tables so that they match exactly the order of the numbers? We'll come up with an argument to say that we can't. So did everyone get the table on the left-hand side? How about the one on the right-hand side? Have you gotten that? All right, so I'm gonna do it. Then I get 0, 1, and then I get 0, 0, and then 0, 1, and then 0, 0, and then 1, 0, and then 1, 0, and then 0, 1, 1, 0, and 1, 1. So, like Joseph said, or along what Joseph said is that potentially we need to reorder the elements, in the rows and the columns, and the multiplicative structure is going to look differently. But my claim is that no matter how we reorder the rows and columns, the multiplicative structure here is different than the multiplicative structure here. Can someone see why that is? And also, I guess the first question is, do our tables match? Is my table correct? And when I'm saying multiplicative structure, it's kind of a loosely defined idea, but somehow you should recognize that the multiplication tables are not the same, up to even if you relabel the elements. But how can you do that easily? This one. Yeah. This one. And you look at this diagonal. Well, potentially I can move this. So in here, what do you see different that's not the same in here?
On the left one, we only have 2 elements that show up twice, and on the right, we have 4 different elements.
Yeah. So in here, in this diagonal, you see all the elements, and in here, you only see 2 elements. And actually, even if you relabel the rows and the columns, the elements in the diagonal are going to stay the same. So it's just going to be reordering the elements in the diagonal. So in here you see only 2 different elements, and here you see all 4 different elements. So that's one way to see it, and that's pretty good. But that's actually not the only way to see it. Can someone else find a way to see that they're different multiplicative structures? And the way that I saw it, it was looking at the anti-diagonal. Not necessarily looking at the anti-diagonal, but I was looking at the number of zeros. So in here, the number of zeros is 8. How many zeros do we have on the right-hand side? 9. So this is going to be... So there's more zeros on the right-hand side than on the left-hand side. So I just counted things. But Emily's argument is still a good argument. There's just multiple ways to look at it. So this is another way to see that the Chinese remainder theorem is non-trivial. Even though you have 2 sets with the same cardinality that each have their own multiplicative structure, there may not be a bijection that respects that multiplicative structure. So in the Chinese remainder theorem, we do have this bijection that respects the multiplicative and an additive structure. And that's what's going on here. So we're going to move on to proving the Chinese remainder theorem. And here, this is a different restatement or phrasing of the Chinese remainder theorem. And it says that if you take M1 through Mk so that they're all co-prime, that each pair has GCD equal to 1, then there exists a solution X to a system of equations, X equals A I mod mi. So this is the equivalent statement of what I phrased originally. And there's also the solution is unique modulo n, which in this case is going to be m1 times m2 times mk. So it's the same statement. It's just another way to phrase it. And we're going to prove this. And in here, actually, I want to make this equal to modulo m. So the proof here is by construction. And the proof really is by constructing the map going from the right-hand side to the left-hand side. This is just what we're going to prove. And we're going to construct that map explicitly to show that we obtain the solution that we want. So in here, we set m is equal to the product of all the little m's, and we set mi to be m divided by the mi. And in here, you should note that since all these mi's are co-prime, and we took out mi from the big capital M in here, mi, then this mi and this mi are going to be co-prime. The GCD is going to be equal to 1. So they're not going to have any common factors. So the fact that they don't have any common factors, that means that modulo mi, we can find an inverse of capital Mi. And we're just going to call that Ni. And then the solution for the system of equations is going to be this x, which is given by this formula. And this is the map that I created to go from the right-hand side to the left-hand side. This is how, if we come back here, so the AIs are going to be this YIs and Y2, and I'm creating a map that maps me this over here. And I had these coefficients 3 and 4, which correspond to this coefficients, the product of M1 and 1 and M2 and 2. And that was for the case that K was equal to 2. So that's how I create the map going back. And then in here, I check that X is the solution that I want. So if I do mod Mi of this quantity, then if I do mod Mi, then for instance, if I do mod M1, then I'm going to get that this mod M1 is going to be equal to 1, and this element mod M1 are going to be equal to 0 by the construction of the capital Mi and capital Ni. So it's this observation. So in here, Mi and I is equal to 1 is by this construction. I just multiply Mi on both sides and I get this identity. And then for j not equal to I, then I have that Mi shares a component, a factor with Mj. So this is going to be, due to this Mi, this is going to be equal to 0. Yeah.
So that's just the same thing as saying just Mi by itself would be equal to 0 mod
Yeah.
MJ?
Yeah, so in here, from here, you actually have that Mi is equal to 0 mod Mj, j not equal to I, because it has a common factor. And so we're going to do 0 times something is equal to 0. And so we can just check every I, and if we check, for instance, mod M2, then this is going to be 0, this is going to be equal to 1, and then the rest are going to be equal to 0. And so what you have is that x is equal to ai mod mi, which is the system of equations that we're trying to solve. And I'm going to leave out that the solution is unique modulo m. It's not too hard to show, and I'm leaving out the fact that the additive and multiplicative structure are preserved. But as we just saw in the examples, it did work for that case, so I expect that you believe the statements. But you can go through the details, and using this representation, this map's actually this inverse map, then you can actually like verify all those the other parts of the claim. So in here I'm just constructing the inverse to kind of show how to go back, and then there's additional details that I'm leaving out. Questions? Now we get to a fun part, the remark about this. What's going on with the Chinese remainder theorem? My claim, or the observation to make, is that this is a Fourier transform, the Chinese remainder theorem. And for instance, let me compare it to periodic functions from the integers to the integers. So functions from the integers to the integers that have period L. Then the Fourier transform says that you can decompose it into different frequencies. And since it's just the integers and it has this period L, you're going to have L different frequencies. And this frequency is going to be, and then this Ci is going to be how much of this frequency is in your function. And this x is also modulo capital N. This is also kind of like a periodic function. It has this periodic structure that comes back every n. And there's different periods. And the different periods are the smaller periods that make up this capital N, are this, or capital M, are this mi. So these are smaller periods that are making up the bigger period. And these are going to be the frequencies. And this is the component of that frequency. Yeah.
Two things. One at the end of the top line, it says A7, and we're using K before.
Yeah, okay.
Anything, it's f of x, where's the x?
XK. XK over L. So this is a different version of the Fourier transform. And this is where that quantum Fourier transform, this is where the structure starts appearing from the Chinese remainder theorem. And this is why one would think about using the quantum Fourier transform to attack this problem. Because we'll see that the Chinese remainder theorem, which is a Fourier transform, is an integral part of this factorization strategy. Questions?
The A never got its K, it's interrupted to talk about the L.
What's that?
The A didn't get its
Yeah. Poor lonely K. A. All right, so we're gonna, now that we have the Chinese remainder theorem, we're gonna be working on putting everything together. And we're gonna do some warm-up exercises. So for now, we've already shown this, and we want to extend this to a generic or a general composite number. So let's figure that out. So the Euler phi function, we defined it, it's given right there. What's phi of p, where p is a prime? Yeah. And do we remember the formula for phi of p to the alpha, where p is a prime?
Minus 1 times p to the minus 1.
Yeah. So now, and do you remember how we proved this? This identity? We looked at all multiples of p in this region and took those out. And we counted by removing all the, if the GCD of x and p to the alpha is not equal to 0, then it has to be a multiple, it has to have a p factor. So we looked at all the p factors and took those out. So we proved that. And now I want to do the similar idea here. And this is what I'm going to have you prove now or work on it. And the idea is that you look at the complement of this. So you write this to be equal to, I believe, n minus the cardinality of the x's, where the GCD is equal to xn is not equal to 1. And you try to control this. So controlling this means that since it's a product of two primes, then you're either going to either have a P1 factor, A, or you're going to have a P2 factor, B, and you subtract those, but then you're double counting the elements that have a P1 factor and a P2 factor. And that's the intersection. So in here, to count this, you can count things that have P1 factors plus things that have P2 factors, and then remove the double count of things that have P1 factors and P2 factors to actually get the count for this set. So I'll give you a moment to try to implement that. Please let me know if you have any questions about that idea. question?
No, I'm just trying to figure it out.
Okay. So the idea here is that we're trying to compute the cardinality, the number of elements here. And the idea is that we're going to split it up into the different components. And just try to do the inclusion-exclusion formula to compute this. So the first thing is the cardinality of A, the number of elements whose GCD with P1 is not equal to 1, and where X is in this range. What's that number? I guess this set actually looks like P1, 2, P1, 3, P1. So it's all multiples of P until we get to the point P1 alpha 1 minus 1, P2 alpha 2 times P1. These are all the multiples of P in this range. P1, P2, P1, 2P1, 3P1, and so on. So the cardinality of A is equal to what? Yep.
I'm kind of confused. So is A that first set on the left that
Yeah.
you have there?
Yeah.
And should those be P1 to the alphas or just P1?
Wait, so A is this,
Okay.
and B is this. And is your question, is this P1 to the alpha 1?
Yeah.
Well, if they have element, so this is equivalent. These statements are equivalent. GCD X P1 alpha 1 not equal to 1 is equivalent to GCD of X P1 not equal to 1. Because if it's true for the alpha 1 case, then that means that they have a factor in common. And since prime P1 is prime, then they must have P1 in common at the very least. So I removed the alphas because
So we're that set on the left of that equal sign there, that's like the complement of the set.
Yeah.
The order of function is.
Yeah. And here, this n is p1 alpha 1, p2 alpha 2. And the idea is that if the GCD is not equal to 1, then that means that the x and this share a factor in common. So it either shares p1 in common or it shares p2 in common. So I split it up this way. And then for A, if they have a factor in common, then it has to be a multiple of P1. So I just write all the multiples of P1 till I get to P1 to the alpha 1 and P2 to the alpha 2. So what's the size of A?
P1 alpha 1 minus 1.
Yeah.
P2 alpha 2.
P2 alpha 2. What's the size of B?
2 alpha 2 minus 1. P1 alpha 1.
Yeah. And what's the size of the intersection?
P1 alpha 1 minus 1 times P2 alpha 2 minus 1.
Yep. Minus 1. So the final formula is going to be P1 alpha 1, P2 alpha 2 minus the cardinality of A union B, and we use the inclusion-exclusion formula. So we do the cardinality of each one minus the cardinality P1 alpha 1, P2 alpha 2 minus 1. So we do the cardinality of each one minus the cardinality of the intersection. And this simplifies. And I'll spare you the pain. And this is going to be P1 minus 1, P1 alpha 1 minus 1 times P2 minus 1, P2 alpha 2 minus 1, which is equal to phi of P1 alpha 1, times phi of P2 alpha 2. Does that make sense? So this is what I wanted you to show, that the structure of the phi function that's multiplicative. And in general, this is the claim. That if you have a phi of a product of primes, you have this prime decomposition, then the phi is going to be, then it's going to be equal to this product. And here we I essentially just, instead of doing it, potentially what you could do is this inclusion-exclusion theorem and just keep splitting it up into different sets. But the Chinese remainder theorem gives us a more straightforward proof. We have that n is equal to our product of the primes to the alpha I, and the fact that the GCD, we have that by the Chinese remainder theorem, the fact that x is the GCD of x and n is equal to 1, is equivalent to the fact that the GCD of each x with pi to the alpha I is equal to 1. So we can, with this dictionary, we can go back and forth. And in here, that means that the phi function was measuring the size of this set. So, and by the Chinese remainder theorem, this says that it's equivalent to the size of this set, where each of them has a GCD equal to 1. So in here, we just, by definition, the phi function is the cardinality of this, and then the cardinality of each of these components is just going to be given by the phi function. So we have this identity, which we know the formula for each of these. We already computed it, which is each of these things in here on the right. So this is equal to I1 to M phi P1 pi alpha I. And here, the way that we're using the Chinese remainder theorem, this GCD, we're using that the GCD here is equal to 1 is equal to the GCD for all these things equal to 1. We're using the bijection, and we're using the fact that the multiplicative structure is preserved by the GCD, by the Chinese remainder theorem. So we can talk about the elements that have GCD 1 here and compare them to the elements that have GCD equal to 1 here. So this really gives us an equivalence, and this really glues the statement together. And what we did before in the previous class is we proved the formula for this base case, and then using the Chinese remainder theorem, we can glue all the cases together to actually get a formula for a general N. And this is the strategy that we're going to do for this proof. That again, we've proved a similar statement for a single prime, and then we're going to prove that by using the Chinese remainder theorem that we can put them together and get this lower bound. And this is going to be the probabilistic part of this is the condition that we need for the factoring algorithm to succeed. And as m increases, as the number of primes increases, then this is going to be, then it's going to be more likely to succeed. So 2 minutes left. In the next lecture, we'll go through the proof of this, and then we'll start a discussion section, a discussion after this, and depending on how much time we have, we might continue until Monday. Any questions? All right, that's it, class.